We are at A2U7L2. We're going to look at exponential function transformations. We just got through looking at exponential function, the parent graphs, and we said there's only two kinds of graphs. There's decay and then there's growth. If b is greater than 1, you have growth, so your graph goes like this. If b is between 0 and 1, you have decay, so your graph goes like that. Now, there's other numbers in your function, though. We just looked at the base function. So when you start putting these other numbers in there, your graph moves around, okay? And we discovered patterns with this so that we don't have to keep graphing every single function. We can just find the parent function and then we can shift it because these graphs get big very quickly. All right. What a sample function might look like with all these additions to it would be negative 3 times 5 to the x power minus 2 plus 4. Let's take this apart. 5 to the x is your parent graph. That's the core. That's where this starts. All of these other numbers shift it around. They might reflect it, they stretch it, they compress it, they manipulate it. But if we can memorize these patterns, then it's a whole lot easier for us to just look at an equation and figure out algebraically what we need to know. All right, your parent function is b to the x. So here my parent function would be 5 to the x. The first thing we're going to talk about is what signals a horizontal shift. Now, a horizontal shift is back and forth right along the x-axis. A number that is added to or subtracted from the variable exponent causes this shift, and we call that number h. That's how we refer to it. So h signifies a horizontal shift. If h is positive, you get a shift to the left. If h is negative, you get a shift to the right. And we're going to get on Desmos in just a second and look at each one of these shifts on a graph. So let's just focus on getting your notes filled out, because you're going to need these rules. All right, k. That's going to be a whole number added to the end. This is what it's going to look like. If k is positive, your graph is going to shift up, and if it's negative, it's going to shift down. All right, if you have a negative sign in front of this, now remember, b always has to be positive. That was part of the definition. So b is positive, but it can be multiplied by a negative number, and what that does is if your graph is going this way, it reflects it over the x-axis. So instead of going this way, it would now go this way. So that negative sign signifies a reflection. All right, the value of this number, the absolute value, if it is greater than 1, you get a stretch. And that means whatever your parent graph was, it's going to stretch it up and make it skinnier. If it is between 0 and 1, a fraction, a proper fraction, it's going to compress it. So that's going to push it down and make it fatter. So let's have a look at our first application problem. We're going to take one with a single transformation, and we're going to see just what effect that transformation has on the parent graph. So let's look at f of x is equal to 2 to the x plus 5 power. All right, my plus 5 here is a horizontal shift. And since it's plus, it's going to be to the left 5. Now, the whole goal behind these transformations is to not have to graph it. Understand that? But I'm just going to graph this first one so you can kind of get a visual on what's happening. And what you want to do is just graph the parent function. So if I just graph f of x is equal to 2 to the x power, how am I going to do that? Well, I'm going to make a little xy chart under here. Pick whatever numbers you want to for x. I suggest, as usual, negative 2, negative 1, 0, 1, and 2. And we're going to fill these in for x. 2 to the negative 2 power is 1/4. Remember, negative exponent, flip it, and then calculate. All right, 2 to the negative 1 power is 1/2. 2 to the 0 power is 1. 2 to the first power is 2, and 2 to the second power is 4. Now let's graph this real quick. Negative 2 and up 1/4 is just a little bit up. Negative 1 and up 1/2 is a little more. 0 and up 1, over 1 and up 2, over 2 and up 4, It's going to be like this, and this is just a rough idea of it. Now let's apply this transformation. So it is going to shift, like I said, this is a horizontal shift to the left 5 units. Find your intercept right here, all right? If this was 1, here's 2, 3, 4, 5, and this is not going to be exact. So it's got quite a bit of shift here. And it's going to go like this. So our whole graph shifted to the left 5 units. Now, nothing else changed about it. The end behavior on both ends is still the same. So let's just look at our characteristics. The domain of an exponential function is your set of real numbers. So that didn't change. The range is the set of y-coordinate values that you have on your graph. Well, remember, this doesn't go past the origin, downwards. So our range is still going to be that y is greater than 0. Now, what's going to change a range is going to be a k value, because that's going to get you a vertical shift. So as long as all you have is a horizontal shift, your range does not change from your parent function. All right, let's look at our end behaviors. As x approaches infinity means as you go towards the right on your x-axis, what happens to your function or the graph? Well, it still gets bigger, so this is still infinity. Now, as x approaches negative infinity means on the graph, as you go to the left, what happens? Well, it still approaches that 0. Okay? Now, your y-intercept. It is just easier for me to take my function and fill in the 0 and solve it to find out what my y-intercept is. Remember, a y-intercept is where x is 0. Now, when I fill this in, when you fill this in, this is not 2 to the 0 power plus 5. You have to do the calculation first. So 0 plus 5 is 5. 2 to the 5th power is 32. So my new y-intercept is at 0 to the right or left and up 32. All right, my asymptote, what line does it approach but never cross? Well, we just figured that up out here for the range. So your asymptote is still at 0. So now we want to identify the parent function, and all transformations found in f of x is equal to -3 times 5 to the x minus 2 plus 1. First of all, to find the parent, that's going to be f of x is equal to 5 to the x. That is your parent. Now, for transformations, you can either go in the order of this list or you can just start left to right. I like to just start at the beginning and work my way through. So my transformations are, this negative means it's going to be reflected about the x-axis. All right, this number, since it's a whole number, this is an a, and it means it's going to be stretched by a factor of 3. So you can just write your stretching and compressing with the word by. So it's stretched by a factor of 3. All right, that takes care of the minus and the 3. This is the base. Okay, that minus 2 up there in the exponent, that's an h, and that means a horizontal shift. Since it's minus, it's going to go to the right. So I'm going to have a horizontal shift to the right 2. Alright, and then the plus 1 at the end, that's a k. K signifies a vertical shift, so it has a vertical shift up 1. Okay? Just go through it piece by piece. Once you pick out this part, your parent graph, everything else has to be accounted for. Everything else means a transformation. So you just follow your rules. They're all right here. And lastly, we want to write an equation of f of x equals 3 to the x that has been shifted down 2 and to the left 7. So we're going to start with f of x equals 3 to the x. Now how do I show a shift down 2? Well, that's going to be your vertical shift. Down 2 means I need a minus k. So I'm going to put minus 2. That will shift the graph down 2. Now how do you shift it to the left 7? Well, that's a horizontal shift, and to the left means you need a plus h. Okay, so that's all you'd have to do. F of x is equal to 3 to the x plus 7 minus 2. And that is transformations. Good job.